My name is Sarah, and we're going to talk about quantum computing today. Let's get started. So, again, my name is Sarah. I'm a PhD candidate at Keio University. I'm in Japan. I study in Japan. And I work with IBM, and I'm a Qiskit advocate. And Qiskit is a Python package that's built by IBM to program and implement quantum algorithm. And I'm also a lead in the Women Who Code Python chapter for a few years now. And I've been working with Women Who Code on so many things. And this is my email if you have any questions about Women Who Code or about quantum or about Japan. Whatever question you might have, you can just send me on my email. Okay, so the talk today, I'm going to talk very broadly about the field of quantum computing. What is quantum computing? Both the status right now of both the quantum hardware and quantum software. How can you get into quantum computing today? And what are the possible job roles existing right now in quantum computing? What do you need to know to get into quantum computing? Like, it's going to be a very general talk, very broad for anyone who's like very curious about quantum or like want to know what's happening, because it's been a buzzword recently and it's been all over the news. We're planning on making further sessions and webinars that is very technical about quantum, about using Python to actually implement quantum algorithm, about some famous implementation of quantum algorithms like Shor's algorithm or Grover, like specific algorithms, and how can we use Python to implement them and then actually run them on an actual quantum computing. That will be next. But for today, we're just gonna cover up a kind of an overview of what is quantum computing, okay? And hopefully answer all your quantum computing related questions. Okay, so let's get started. You can start writing any questions you may have while I'm going through the slide, and then we can go through them after. So first, let's see what the word quantum means. So quantum means very small, or it's a word used in physics when we want to talk about very small stuff like atoms or particles or electrons. So stuff that is very small and have their specific set of rules of physics that is kind of very different than the rules that applies to our daily lives, right? A quantum computer is a machine or a computer that uses these special laws that it does not apply in our lives to solve problems, solve complicated problems. Let's put it like that. So the field of quantum computing, or we call it QC, right, is relatively new, as in practically relatively new, or even like if we look about how like the advancement of computing happened since, you know, the 1800s, quantum computer has been like a relatively new idea. And although quantum physics existed all along, no one actually thought about quantum computing seriously until 1994, if I remember correctly, when Peter Shor introduced his algorithm, right, that would break the encryption system of the internet that we use now, and that kind of give people the push they needed to take quantum computing seriously. Because if it's gonna break, like, let's say like the most secure algorithm we have right now, then maybe it's something that is worth, you know, investing in or like following through. But since 1994, it's been very theoretical field, and it only existed in research labs, right? And like nothing was very practical. There was not actually a quantum computer that exists and people can use until like recently. And by recently, I mean very recent. In 2019, was the first quantum computer that was introduced by IBM. And since then, IBM has put in a lot of effort into developing their quantum hardware and software, and even like a lot of effort in introducing people to quantum, and actually like putting on like some great learning materials for those who's interested in joining quantum computing. And when I say the first quantum computer, I mean like even a quantum computer that you can use. So IBM has different computers right now that you can access through the cloud, through something called the IBM Q experience. And through this website, you can actually run actual code on like the quantum computing computers built by IBM, and you can get the result and work on them. The results are not good, and we're going to talk about that in a second. But for now, yes, there is a quantum computer, and no, it cannot do fun stuff yet. There's like, I feel like the most common 2 questions I get about quantum. Okay, so why do we need quantum computers, or why do they matter? How would they make a difference than the classical computer that exists right now, that I would say are doing a pretty good job at what they do? So the first, maybe, and most important reason is that they're fast. There are some problems that will take classical computers years to solve. And if you guys are like familiar with complexity theory, right? We have the MP problems and which is the complete, the MP, and there is MP complete and all kind of problems that is hard for classical computers or the computers that we have right now to solve. And by hard, I don't mean that they cannot solve them. I just mean that it will take them years, maybe like 100 or 1,000 years to solve one problem, whereas if I use a quantum computer, it will take very significantly less time. So the speed is one of the most important thing about quantum, or one of the strongest advantages of quantum computers. They can solve complex problems. So they can solve problems, again, that is harder for computers now to solve, even for supercomputers. Whether the difficulty comes from like the exploration of answers or the time needed to reach the answer, both those things can be solved by using a quantum computer. And they can run complex simulations. One of my favorite quantum quotes is by Richard Feynman, and it says, "Nature isn't classical. So if you want to simulate nature, you should make it quantum." So nature is quantum. Everything in our daily life is quantum, if you thought about it. And so if we want to simulate anything that happens in our daily life, like for example, the weather, natural disasters, global warming, all of the things that exist right now in our daily life, it is quantum. And even though classical computer has been doing a good job at approximately simulating them, if you want a better and a more accurate simulations, then a quantum computer will be more fitting for that job than a classical one. Okay. So how does quantum computers work, or what are the basics of quantum computers, right? Like what makes them different? And for that, we're going to talk about the 3 pillars of quantum computing, which are the 3 core concepts that quantum computers work on. First of all, we're going to talk about qubits, or quantum bits. Qubits are the equivalent of bits, which is short for binary digits, which are the zeros and ones that exist in like today's classical computers, right? Everything today in the normal computers is either 0 or 1. In quantum, it's called qubit, which is just add Q before the bits. Okay, so qubits, the difference between bits and qubits is actually very interesting, or the way I like to describe it is this. In classical computers, bits are more of a concept rather than an existing thing in nature, right? The 0 means there is no current in the circuit, or if you think about it as switches, the switch is open, so there is no current passing in the circuit. If it's 1, that means the switch is closed and there is a current passing in the circuit. So they're more of a concept rather than something that exists in nature, right? Or that is existing in our world. However, qubits do exist, because as we're going to talk like in a bit about the construction of qubits, or what type of qubits there are, qubits are actually like something, I want to say physical, but like, you know, like there is an electron and it's spinning, so that's a qubit. So the electron, like for example, the spin of electron represent a qubit, or the electron itself, or a photon, a light photon can be a qubit. So qubits kind of do exist in a sense that they are a representation of something that does exist in nature rather than a concept. And again, because quantum is like we're dealing with this electrons and photons, they can be, okay, at 2 states in the same time, which I guess where most of the confusion about quantum happens, when people say, hey, it can be both 0 and 1 in the same time. And this is only partially true. they can be both in the same time during computations, but when we measure them or when we want to know the result in the end, they can either be 0 or 1. And that leads us to superposition, right? Which is when something can be both 0 and 1 in the same time, right? So we just said like that partially or during computations, qubits can have both values of zeros and ones in the same time, which is called superposition, right? And there is like the famous thought experiment, which is Schrodinger's cat, right? Which is like there is a cat in the box and there is poison with the cat. And until we open the box, we can never know for sure if the cat broke the poison and died, or if it's still alive and the poison did not leak, right? So here it's kind of like probabilistic, right? Like it's either the cat is 50% dead or 50% alive. But once we open the box and see exactly the state of the cat, then we'll know that whether the cat is actually alive or dead. It cannot be both alive and dead in the same time once we open the box. But before we open the box, you know, we can just guess, right? And this guessing is what superposition is pretty much. Another way to explain how like everything in life is quantum, especially the superposition, is thinking about what you want to eat for dinner. And if I may say like that thinking what you want to eat for food is one of the most complicated things to think about. What should I eat today? And if you think about it, before you actually decide what to eat, your options are in a state of superposition, because theoretically speaking, you can choose to eat anything. You can choose to eat Thai, Chinese, Japanese, you know, burgers, pizza, whatever food you want. And until you choose exactly what you want to eat, technically, all options are available, like there exists in superposition. And we can say, mathematically speaking, that it has a uniform distribution, which means like that the probability that you would choose any of the cuisines are the same. Of course, in practice, that is not correct. I mean, maybe you hate Thai food or Japanese food, then the probability for those will be 0. But nevertheless, I hope like you get the idea of what I'm trying to say, which is, you know, they exist in superposition. You can choose whichever. There is a probability for each of them. And until you for sure decide on one, all of them do exist. And that's superposition. That's the same as Schrodinger's cat. Cool. So far, do people have any questions? I love all food. I agree, Stephanie. Food is great. Okay. If anyone has questions in the middle, as I said, just keep posting them and I can pause in the middle for questions, especially if it affects like your understanding of what's next. Okay, so that's superposition. The third and final pillar of quantum computing, which in my opinion is the most confusing one, is entanglement, okay? Entanglement, I think there's another picture there that I forgot, but entanglement is a phenomena that kind of creates a correlation between two qubits. And you can think of entanglement as kind of like having the qubits be in a relationship, right? So now they're affected by each other rather than being independent, right? And entanglement can be created using different ways. For example, if you're using photons as qubits, we can create entangled photons by making them come out of the same light source. There are more complex ways to create entanglement, but just say entanglement creates a relation or a bond between two qubits. So now they're dependent of each other rather than independent. So the states that they can be, which is like 0 or 1, now they're very dependent on each other. So if one of them is 0, the other one must be 1 and vice versa. Like they cannot be both 0 at the same time or 1 at the same time, okay? That is pretty much what entangled is. It just makes the qubits dependent on each other. And that kind of creates the whole probabilistic thing in superposition and in quantum. I think there's a question. Is there research we can check out to give us a better idea of how qubits work? Yes, there are resources, and the resources are in the slides. I think we can share the slides with the attendees in the end, and you guys can check the links there. Okay, we're going to talk a little bit more about qubits now, so hang on tight. Okay, so those are the 3 pillars. So if we have qubits, those qubits can be entangled and they can be in superposition, and that will allow them to do, you know, what I like to call the quantum magic, right? Which is solve the complex problems. Okay. Okay, let's talk about qubits a little bit more, right? Because they are very essential. They're the core part of quantum, right? Qubits. So what are the types of qubits that exist today? So qubits, since quantum is still a new field, there's still a lot of research going on what can be used as qubits, what is the best kind of qubits to use, all of this stuff. It's still under research. But today we're going to talk about like the 4 top, like let's say categories of qubits. Okay, we're going to talk about spin qubits, trapped ions and atoms, photons, and superconducting circuits, or superconducting qubits as they call them. Let's start with the spin qubits. Okay, so we're talking now about the different ways we can make a qubit. Okay, so a spin qubit, which is when you take a particle, right, and the particle has an orientation, right? Like often like particles in nature are spinning. They're not very constant, or they're not still. They're spinning either like clockwise, anti-clockwise, like they have a spinning orientation. Like do they point down or point up, right? Based on that spinning, they can generate a magnetic field, and the direction of the magnetic field is what we're referring to here as the spin, right? So based on how they're spinning, if they're spinning like anti-clockwise, for example, the magnetic field will be pointing up. If they're spinning the other way around, then it will be pointing down. And based on that, we can say, cool, now we have this particle or electron as a qubit, right? And if it's spinning up, that means it's 0. And if it's spinning down or pointing down, then it's 1. Okay, and with that, we created a qubit. Cool, that's like one type of qubit, okay? Spin qubits. Another type is trapped ions and atoms, and actually Google is one of the companies that work on trapped ions, qubits, in making them. So in nature, again, chemistry, high school chemistry, right? We have like a nucleus, and then we have the energy level, and then the electrons are often spinning. But if the atom is just existing, right, like there in nature, nothing is happening, there is no excitation, there is no any chemical reaction, right? The electrons are often in the lower energy level. But as we studied in chemistry, or as if we didn't, if we excite them, as in we give this atom some energy, the electron will absorb this energy and then move on to a higher energy level, right? So we can use which energy level the electron is in to be the state of qubit, okay, or to be a qubit. So if the electron is in like a lower energy level, then it's 0. If it's in a higher energy level, then it's 1. Okay, that's another way of making qubits, right? Like, so we're going to use like where in the atom is the electron, and based on that, we can define if it's 0 or 1. And then we have photonic qubits, and photons are light particles, right? And photonic qubits is actually one of the largest areas of research when it comes to like constructing qubits. And there's different ways of using photons to create qubits. But here I'm going to talk about just one, which is like the magnetization, okay? This one is very similar to the spin one, but here we're talking about the particle itself, and we're talking about the polarization of the particle. It's either vertically polarized or like horizontally polarized. And we can use this polarization to make it 0 or 1. Okay, so the photon is like the light particle, like laser particles, or whatever light. There's so many research about this. Use different light sources to generate the particles or the photons. And then we can see their polarization, and based on the orientation of the polarization, we can say it's a 0 or it's a 1. Okay, and then there's finally the superconducting qubits. I don't know if anyone here ever tried to Google, like, you know, quantum computer. Have anyone tried in Google, just like Googling quantum computer, and just, I want to know what is like the images that shows up. I'm just curious if anyone remembers anything, right? If someone tried to Google quantum computer, right, the difference is, we'll answer that, Vanessa, in a second. Yes, like a large computer. Yes, large golden computers. It's something like a chandelier, right? That's probably like one of the first pictures that you're going to see in Google when you when you Google quantum computer. And actually that chandelier is a superconducting qubit-based quantum computer. And it's called the quantilier, actually. And it's basically that chandelier is just a fridge, because to make superconducting qubits, basically we use specific materials, right? Specific materials that when we cool them down to a specific degree temperature, okay, they start being conducting, okay? And then we can see based on the current that's passing, whether if it's clockwise or anti-clockwise, we can say it's 0 or 1. And superconducting qubits are the basis of the IBM quantum computers, all of them, the ones that are available now, the one they're still building. They're a very big fan of superconducting qubits. So the quantilier is actually using superconducting qubits. And although it looks so big, the actual quantum computing part, like the qubits themselves, are very small. There is the small part in the middle or in the bottom. The whole thing is just a fridge to keep it in a very low temperature. So actually the materials will be superconducting. Because if the temperature drops, then the material will not be superconducting. There will be no current in the circuit, and then basically it won't work. So they need to stay in a specific temperature. Okay, now let me answer Vanessa's question. How is the cutoff between 0 and 1 determined between the level? Is it standard? I'm guessing you are talking about the energy level one, right? Like the trapped ions. So often in the circuit, in the atom, we kind of specify a range. So we say if the electron is within this range around the nucleus, right? Then it is like energy level 0 or like a low energy, right? Or if it's between another range, right? Then it's 1. So technically this is not standard. It depends also on the materials using, like what kind of ions, right? Or atoms are we using in this case. But once like the material is chosen, then for this material, there is a standardized like energy level, like the range of energy level, that if it's in this range, it's 0. If it's in that range, it's 1. I hope that answers the question. Okay, so these are qubits. Does anyone have any questions about the construction of qubits? Again, as I said, qubits are still undergoing a lot of research, right? There's a lot of things that the researchers are still working on, making better qubits. As we just saw, like these qubits that we talked about are like tiny stuff, like they're like electrons or photons or like a molecule, like all very small stuff. And because they are very small, they are very prone to errors, right? Specifically, if I will consider something like, like the spin qubits, right? Like how they're spinning, and because they're affected by electromagnetic waves, some random electromagnetic wave can hit them in the middle of computation and kind of like messes up the computation that they're performing, right? It's one of the reasons why quantum computers now are not very accurate. It's because all these qubits are very sensitive, right? Like the trapped ions one, again, because if they get any random energy from the air, right? Because we have energy all around us, they can change their energy level and then will mess up the computation. Same for the superconducting qubits, right? They have to be in a specific temperature, and they also affected by, again, electromagnetic waves and so many things. So all of these are very fragile. These qubits are very fragile, and that's what makes building a quantum computing hard. I think I have a... Yes, what temperature level? Oh my God, that is a very great question. I am not sure exactly the temperature, what it is, but it's very cold. Like, I don't know, I think it's minus something Kelvin. Yes, it's a very cold temperature for them to be superconducting, right? If the temperature just, like, if we put them, like, say, in a hot room or something, it will not work. That is the superconducting one, right? Specifically. The other ones do not need the temperature much because they depend on other stuff. Okay, so the superconducting qubits is the one that needs the temperature to be in a specific temperature for them to work, right? It depends also on the material, right, that is used, because there are different materials in nature. that can be superconductors if we cool them down. So it depends on the material. Each material has its own threshold of what the temperature is using, what temperature they need to become superconducting or to, transfer current. That's one way to put it. Okay. So what is the state of quantum hardware today, right? So we have this whole different ways of making qubits, right? And there are different companies and startups, right, are working on building quantum computers, like from Microsoft to Google to IBM to a handful of startups that are just wanting to build like a quantum computer that will actually do what we want it to do, right? Which is solve these complex problems that classical computers today can solve, right? But what exists now? So now what we call, but by we, I mean the researchers, not me personally, came up with this name, which is noisy intermediate scale quantum, which is NISQ. We call it NISQ, right? NISQ quantum computers, right, are quantum computers that are noisy. Again, noisy refers to how sensitive they are, right? We just talked about this. Said like those qubits are very sensitive and very error prone, right? They're not good enough to kind of like avoid error and still do what we want them to do. So they're very noisy, very fragile. And the intermediate refers to how many qubits we need or we can put together and actually perform a circuit. And it's like 50 to 150 qubits. And just to give you an idea of like how far quantum needs to go to actually be useful is if we want to implement Shor's algorithm, right, which is the algorithm that breaks the RSA, which is the encryption system of the internet today, we need at least like millions of qubits. And right now, people are still trying to work on making 50 to 150 qubits work, let's say with a minimal error that it will provide like useful computations. So this is still under the work. Still, we don't have a quantum computer that is accurate and will actually give us like good results, unfortunately, but people are working on it and they're making very great progress on the hardware side. Since quantum started becoming like a buzzword or like very something that people are interested in, or like, let's say big companies are interested in and governments are interested in funding, hardware has been taking most of the attention of the research, right? Or of the funding. So the hardware aspect of quantum is moving way faster than the software aspect, which we'll talk about in a second, because everyone is like, hey, we just need to have a quantum computer that actually works, and then we can focus on the software. So, but they're doing a very great job, like a lot of breakthroughs recently, which is very nice and like exciting about the future of the field. Okay. So that's the hardware aspect of quantum. Okay. Again, it's still under development. There are different ways, right, to use quantum. There are some companies out there from the companies that's building quantum hardware like IBM, right, and Rigetti, that you can use their quantum hardware, like you can write code and then like over the cloud send it to the quantum computers and then get some results back. It's something that exists right now. So they do exist. If you want to play with them, they do exist and you can try something on them. They're very faulty, which means that the results that's coming out of them, even if you're using very few qubits, are often just noise, unfortunately for now. But they're working on how to overcome that. And since this is women who code Python, right, and Python is software, I did not focus much on like how do they deal right now with the errors that happen from the hardware. But if it's something that people are interested in, we can talk about that in another talk, which is like, quantum error correction, which is like how do they deal with so many errors and noise happening on the hardware level, right? It's a very big research field, and we can talk about it if people are interested in that. But for now, let's move on to the software side, okay, which is, I would say, doesn't have as much effort put into it as the hardware side for quantum, unfortunately. But today, if someone wants to like implement a quantum algorithm today and run it on like one of the existing hardware, what options do they have to write code, right? I want you to think about quantum now, like especially the software aspect of it now, as kind of similar to the early stages of classical computers, but instead of having to write your code in zeros and one, which is assembly, you're actually writing it using like a programming language, but you're describing a very low level of the circuit, like you're describing gates and registers, which is basically what people were doing back in the early stages of the classical computers, but with zeros and ones, right? Now we don't even need to think about transistors and registers when we write software for classical computer. And hopefully at some point in the future, quantum software will reach that level as well, which is a level where we don't have to worry about like the hardware aspect of quantum, and we can just focus on like just implementing algorithm. We don't have to think about registers. But for now, that's what we have to do. So you can implement a quantum circuit or algorithm now, either using some programming languages built just for quantum, and there are a few of those exist right now, or the most commonly used approach, which is to use a package or a library that's based on a classical programming language, or you can use something like lower level, and that is often used by like physicists and mathematicians, right? They're used like special kind of math, or use like the quantum assembly language, right? To describe the circuit, or pulses, which is like waves, right? Because quantum has a lot of waves, electromagnetic waves everywhere. So you can use that to describe a circuit, but it's like a very low level approach and require you to know a lot about the algorithm and about the quantum physics and mechanics that empowers it, right? But if you don't, but you still want to play with quantum, you can still do that using like Python, right? Or using even a higher level quantum programming language, like the ones we're gonna talk about in a second. Okay, so as I said, this is the most common way to do it, which is using a classical package, right? Or like quantum packages built on classical programming languages. Today, Python is by far the #1 programming language used in quantum, right? And the most famous Python packages are Qiskit, Cirq, and Biquil. So Qiskit is built by IBM, Cirq is built by Google, and Biquil is built by like a university. I think it's a university effort, right? Like so, a researcher built Biquil. Yay, Python! Yeah, Python everywhere. It's so great. Big fan of Python. There are also, if like you're not into Python, because some people don't like Python for a lot of reasons, none of them make sense to me, but if you want something C++ based or Java or even JavaScript based, there are different quantum packages on different classical programming languages, not just Python. I'm just saying that Python is the most commonly used programming language. But if you're into any other programming language and you're not comfortable with Python, you can also get into quantum without actually having to use Python, if that's what was stopping you. So they all have a similar thing, right? Which is basically you're gonna use these programming languages to describe a circuit, like put some registers that have some qubits in them, and then lay out a series of gates. Okay, that's basically how programming quantum computers work now. You just lay out a series of gates, right? You're just gonna put gates, and gates are like the basics of even classical computers, but now we don't think about them. But in quantum, we are at that stage for now. So you're gonna just lay out a series of gates, but the difference is that now you can harness the power of the classical programming languages, like you can use for loops or if else conditions, right? You do not have to be like use like an assembly level programming to actually lay out these gates as people used to back in the early stages of of classical programming or classical software, like that. Or you can choose to use programming languages that is just built for quantum, right? Or like people designed it just so people can use it on quantum computers, like Q# that is built by Microsoft. There's Quibber, and Quibber is very similar to C++, I would say. And there is like the newest one that was, I guess, Slick, was published by ZHC Zurich, I think, the university. And they did it in 2020, I think late 2020 or like early 2021 when they released SLIC, which is just a high level representation, right? It's a high level programming language that has similar syntax, kind of like a mix between C++ and Python, and it is for quantum. And the good thing is if you choose to like, you know, learn one of this new programming languages to actually like implement quantum algorithm, these programming languages will get compiled, right, to quantum assembly, and you can actually use these programming languages to like write software, say for the IBM machines, for example, even though none of them are built by IBM. So you can still use them to implement on actual hardware for companies that allow you to use their hardware, because not all companies allow you to use their hardware. Like for example, Google does not let people like accept the people who work in Google to use their quantum hardware. Okay, so they have like some similar syntax. Some of them are easier than the other. SLIC, since it says the latest, they try to make it as simple as possible to describe a circuit, right? Here I just have like these code snippets, right? They're describing the same thing, but like in different languages. It's the same thing as described here using the quantum packages of classical languages as well. So, you know, just like for you to have an idea of like how many lines of code and complexity to write in like the different ways. Other than that, you can like choose to use a very low level approach to program, which is like using the quantum assembly or QASM as they call them, okay? Which is you can use like, as I said, like open pulse, which is using the waves. You can use the QX simulator, which is a simulator from the name that you have to describe, like using, you know, very, very low level descriptions to add like the gates to the registers. Or you can use something called ZX calculus, and ZX calculus is like a field by itself, and it's like just like a mathematical approach to describe quantum algorithms, okay? Now, all of these are options that you can use based on your comfort around quantum physics, quantum mechanics, the algorithm programming, right? To implement and try or experiment with quantum algorithms on like actual devices. But none of them, I won't say, oh, this is better than this. It depends on your comfort, what are you're comfortable with, sorry. So it depends on what you're trying to do, where you are at your like quantum. If you're just getting into quantum, maybe you don't want to like start with quantum assembly, right? You can just start by like understanding the basic of quantum and using like Python or C++ or JavaScript, right? And implement some algorithm and then learn from that. And then once you feel you're more comfortable, you can then go a little bit to a lower level if you want to better understand what's happening in the circuit. Or you can just use the level of abstractions that is built, like those classical programming languages or like the programming languages that is built particularly for quantum. Okay, so what do you need to know, right, to get into quantum today, or what do you need to have? First of all, I feel like, and the most important thing is you need to be curious. And I'm guessing like the people who are here today are curious about quantum, about the field, and about what it has to offer, right? So once you're curious, you have this curious mind, it will take you a long way. Because if you're curious, you're going to put on a lot of more effort to learn new stuff about quantum or about anything in general. Okay. I would say basic knowledge of electronics, like, you know what gates are, because gates are also one of the building blocks of classical computers, like AND gates, NAND gates, transistors, right? They all exist there, right? But we now just have so many levels of abstractions above of it in classical that we don't need to worry about. But if you know a little bit about that, especially if you're interested in the hardware side of quantum, then it's something that's it's knowledge that is important to know. Okay. Now you may ask, hey, if I'm interested in software, but I do not know anything about electronics, can I still do it? I would say the answer is yes, because then you will just have to know what are quantum gates and how they work, and then you can just go from there. Right? I'm saying that if you do have some previous knowledge, it will help, but if you don't, you can still do it. Okay. I think one of the main concerns that people have when they think quantum is how difficult the math will it be in the field, right? Now, I would argue that the math in quantum is not more difficult than, for say, the math in artificial intelligence or any of the data science branches. I would say even in data science, there are even more complex math than there is in quantum. Like quantum built on two core things or two core math branches, linear algebra and probability theory. Linear algebra is used to describe everything in quantum systems, starting from the qubits themselves to the circuit. And probability theory is because I said everything in quantum is probabilistic. So you need to know how probability theory works because everything in quantum is probabilistic. And also, if you know the basics of probability theory, you will go a long way. You do not even need to know the advanced part of probability theory to get into quantum. Okay. Now, the knowledge of the basic of quantum physics. Now, I'm going to be honest. When I joined quantum, I did not know much about quantum physics, and it was fine. Right now, I've been doing quantum for a couple of years, and I still would say like the areas where I needed to know a lot of physics, quantum physics, to actually understand something, it's not that much. So although it's useful, I would say you won't need it as much, okay? And of course, if you want to do something software, you need some programming knowledge, or you can just learn programming to, do quantum, also an option if you never programmed before. But if you know Python, for example, already, you can now, after the session, just go install Qiskit and start programming quantum algorithms and running them on the IBM devices. You can just do it right now. So it just will help. Like all of these stuff will help you, I don't know, like say speed up your journey in quantum, but it like lacking one of them will not stop you from pursuing quantum. Let's just put it like that. Okay. Cool. Awesome. So let's see like the roadmap for quantum, right? So as I said, there are different kind of companies, right? There are so many companies that are trying to build quantum. And this here like is from, I think, an article that I read about like where is quantum going, okay, till 2026, which is very close, like it's 4 years from now, right? And people are hoping that by like 2026 we'll have more qubits, right? Like as you can see the numbers here. Now, there's something that you may notice here from this, right? Like you see stuff, let's say, hey, 7 qubits, 28, and then there is 5,000 qubits, right? And then here there is 433. And then you might say like, hey, why is it like going backward? Like obviously D-Wave has like 5,000 qubits, right? Was like in 2020. And IBM still trying to get like say like 2022 or 2023, like 433 qubits. Like what's happening there? Well, D-Wave does not build quantum computers in their, I would say, like in the sense that you would imagine, right? That is, they're trying to build a specific purpose quantum computer, or like you can think of it like embedded systems, right? Embedded systems are small classical computers that are built to do one specific task. That's what D-Wave does. So they're building small quantum computers that are for specific tasks. And if you just make them task specific, they become easier to build in a sense that you do not have to worry much about the construction or changing it. But like say IBM, Rigetti, Google, all these companies, they're trying to build a general purpose quantum computer, which means something like, like the laptops we have today, but like in a little bit less broader sense, but something that you can use to implement any algorithm and not just something specific. And those are more harder to build because they need to be more versatile. Okay, that's why like there's this weird change in like the number of qubits. Okay, so this is like where quantum hardware is going, right? Or the future of quantum hardware. I would say so far we are kind of following this map from the perspective of like the number of qubits. So that's a good thing that we're not falling behind. In fact, in some companies are like doing it earlier than what's anticipated in this graph. What about software? As I said, like quantum software has not been having much attention, or like the attention for quantum software has started very recently, which is when we started having a somewhat working quantum hardware, right? Or quantum computer. Then people was like, oh, maybe we need to develop some software now. So there are so many things that needs to be done in the perspective of like the software. We need to build compilers, we need to build libraries, we need to be able to navigate the noise or the error, right? In both, like NISQ is what we said now, the current era of quantum computer, which is like the noisy intermediate one, or FT, which we would call the fault tolerant. So there are the future of quantum computer, which can have like are more like less prone, let's say, less prone to errors and more tolerant towards like those noise. Okay, we need to know what data, we need to build simulators, debuggers, profilers, everything. And actually my PhD thesis is about like kind of like getting an idea of what would it be, or how would a quantum debugger look like. So I'm working on the debugging aspect on the software side of quantum computer. So yeah, as for the question about resources, so there are different resources like articles you can read about the different concepts of like about superposition and entanglement more. You can read more about quantum computing, like in general, right? Like why do we need it, the advantages, disadvantages. And the Institute of Quantum Computing is the place where I got the graphs of the different construction of qubits. And here, like Program Quantum Computer Today is an article I wrote about, like has more details about like different ways to program quantum computers. And what do you need to get into quantum, like more, again, specifics about what exactly do you need within the math. And I would totally recommend, if you really want to get into quantum, to check out the Qiskit book. It's a free book online that will take you from everything from the start to quantum gates, to quantum circuits, to the implementation of quantum algorithms, to even advanced stuff like, you know, error and optimization. And Qiskit YouTube channel also have great materials. IBM has been doing the Qiskit summer school where they focus on a specific topic, and they put the lecture links on their YouTube channel. So if you have time and you're curious, definitely recommend checking that out. And that is what I have for today. I talked a lot and my throat hurt. I hope you have a lot of questions, because that's what we're here for, to answer as many questions as we can. You know, does IBM charge to use their? No, there are free. You can just go to the IBM Q Experience and make a free account, and they have computers that are free for anyone to use. They have also computers that you have to be a partner or like working with them to use. But if you just want to like get a sense of quantum, they have computers that people can use for free. Yeah. And then we have two more questions in the Q&A. What are some of the things we need to be concerned with as quantum computing becomes more developed, for instance, in the background? Oh, well, yes, I would say concerned is a very interesting way to put it. I would say, hey, like we are now, people started getting into quantum, right? Or like focusing on quantum because it's potential to break the RSA, right? So if I can like use quantum to break the RSA, that means I can use it to make a better encryption system, right? So I can say, sure, quantum will make a lot of security stuff go obsolete. It can also help with the networking aspect, right? Like the internet, just not just the security aspect of the internet, but the network layer itself. It can make it better. So yes, of course, it can in the future, when we have a fault tolerant quantum computer that can do anything, can break some of the stuff that we have classically. And notice, I'd say some and not everything, but it also can help it make it better. So it's kind of like a two-edged sword, kind of. I hope that answered the question. So concern is one way to put it. Another way you can say, oh, it's an opportunity to make it better. What work is being done related to security, more advanced encryption system? Oh, there are a lot of work. Quantum encryption, quantum cybersecurity is a big field. Unfortunately, I do not know much about it, but it is a big field, and there is a lot of people who are focusing on, like, you know, what they call post-quantum encryption, which is what we do after we have a quantum system that is good enough, and then we can make new encryption systems that are better than the one we have today. So it is definitely a very big field, and if you're curious about it, I can send you some, again, resources to read about. if you reach out to me, but for now, like, I do not know much about it. Yay. Any more questions or concerns? What are some practical application of quantum? Oh, man. Okay, let's answer that one first. Quantum has great potential in helping with the search problems or things that requires kind of looking into a lot of possible answers in the same time, like, for example, I would say anything data science, like from natural language processing to machine learning and artificial intelligence, because they require examining a lot of data and a lot of possibilities, which is the strong suit of quantum, the fact that it can exist in all possible answers in the same time. It will be a great practical application for this. Also, it have the potential to make some search problems like graph theory problems. Graph theory is a branch of math, and it's used a lot in networking, like connecting nodes, like, for example, have more efficient networks. Quantum, since it can search a lot of stuff in the same time, it will have, it can make things faster, right? And when things become faster, hopefully, I don't know, be better, although faster is not always better. But in the case of this particular application field, which is like search problems or like security, it's like one of the two major things I would say. I'll also say chemistry. Chemistry is one of the most like think about making medicine, right? Because like when people research making medicine, right, you need to think about like how the molecules and how the materials connect with each other, like what a connection will result, like, you know. Quantum chemistry is pretty much one of the main reasons quantum is still going, because the way it can, like, let's say, predict like the interaction between chemicals, or like help us make better drugs or faster drugs, let's say something kind of like for COVID, the vaccination, right? Because it can simulate things faster, right? And it can test more combination than a classical computer can, faster than a classical computer and more efficiently. And so this will be like, I think, a very great field, a practical field for quantum. Okay, there is a question. Can the QC library run on Colab? Yes, all the Qiskit, particularly Qiskit and Cirq, both of them can run on Colab and can run on, like, you know, Jupyter Notebook. So definitely they can run on Colab. Also, if you don't want to like have something in particular downloaded, as I said, if you go to the IBM Q experience, you can actually write code in the browser, and you don't have to download anything and worry about anything. Okay. I think, so how do I reach out? If you want to reach out to me, I have my email here. You can reach out to me on my email. Yes. So please do reach out. I'm happy to help anyone who's curious about quantum or anything. So yeah, thank you for the questions. They were very interesting. And I do hope that you would consider quantum, because I think it's pretty cool. And I think right now is the most optimal time to join the field, because we need more people who are like passionate about like taking quantum to the next level on all aspects, hardware, software, all aspects. Also, like, the community now is great, and because it's not that huge yet, right, you can still you can reach out to practically anyone in quantum, and I'm pretty sure they'll help you, because they helped me, right? And if you're ever curious about doing a master's degree or PhD in quantum, you can totally apply to my lab, which is called Aqua. And if you want to come to Japan, you know, so definitely. So please do reach out. I'll send you whatever information you want. And yeah, you can also find me on Slack, by the way. If you're on the Woman Who Code Python Slack, I am on Slack. If you're not an email person, and on Slack, I am like Sara Metwalli. So if you want to find me on Slack, you can also find me on Slack. whatever way you want to reach out. And now I'm going to shut up because my throat hurts. But thank you everyone for coming. I really appreciate it. And I hope you enjoyed it. And I hope that now you know a little bit more about quantum than when we started. You're welcome. I'm so glad you enjoyed the session.